Hi guys, welcome to the next video. So the next video is the another type of joints, which is reinforced and plate reinforced concrete bearing. So we have embedded plate here, and then it's reinforced inside the beam or component, and then you have stirrups to control to resist uh, forces. So uh, if applied bearing stress exceeds the value, keywords exceeds the value in equation 8.2 and 8.3. So bearing plate, so you have two component bearing plate and reinforcement are required in the bearing area. So the bearing area here need to supply plate and reinforcement as shown in figure 811. Horizontal force here exists due to frictional restraint against thermal movements. You have thermal movement and shrinkage with the presence of vertical force. So the beam is heavy, so and the weight, self weight, and then the thermal movement due to changing of temperature will cause horizontal forces that needs to be kept in your design. So to calculate that, we correlate with the vertical force. So vertical force times static coefficient of friction, so you get your horizontal value. So these are the values. So for mu, the coefficient of friction, steel to concrete is 0.4, concrete to concrete hardened 0.7, and concrete to hardened concrete as 1.0, and then monolithic concrete is 1.4. Discuss monolithically, we discuss in situ. So in the case of cracked concrete bound by reinforcement, an effective shear friction mu naught mu prime is used. So if there is a cracked concrete, this usually for post tension or pre stress component, because usually involves once you stress or apply a compression, post tensioning. If you once you post tension the cable inside the post tension beam, uh, the beam will become haunch, haunch, and then crack may appear. So if that happens, so your value of mu would be based on the area of concrete and the value of h. So there is a mu prime. You need to calculate for mu prime. So your value is slightly different. If yield strength of bars AH is FYH, your main bar area of steel is FYH. So usually this is for Z0. This because it's your main bar, high strength steel. Or in this case is taken as 250. If they are welded to the bearing plate, then AH is equals to uh, 0.9 V divided by 0.95 FYH cos theta times mu prime. So this is your vertical forces, and this is the bearing, the modified uh, uh, modulus of elasticity of the steel. And then for your shear links, H divided by 0.95 FYV mu prime, or you can correlate with AH value, which is AH times FYH cos theta FU, because your H value is based on your V. That's why you can derive another form of equation for 8.9. So the thickness of a bearing plate or angle section should be sufficient to resist force H, but this will be found to be rather small, and therefore minimum thickness of 10 mm is used. So usually friction is restrained by the plate. If it is steel plate, 10 mm is uh, the minimum thickness is 10 mm because If you use rubber, for example, and then you will see more deformation. Like if you see plate 10 mm is uh, enough. And based on the standards, corrosion protection requires a minimum thickness of 4 mm, so use that satisfy corrosion protection and also the horizontal friction forces. So let's take a look at the example. Example 8.5, you have a precast beam of 6 meter long, 400 deep, 300 mm wide. So your beam, precast beam, 6 meter long, 400 deep, and 300 wide. Basically 6,000 will affect the tolerance, constructability tolerance. And the beam is supported over a length of 100. So this is your bearing length, 150 mm on dry bearing. Dry bearing, so it's a dry bearing, so you have a condition of 0.4 FCU. That's your limit. Dry bearing. Let's take a look at the previous slide. Dry bearing here. So you have a dry bearing. So you are limited to 0.4 FCU. So if the ultimate end beam reaction, so reaction is being calculated by the question 400, you have the ultimate end beam reaction is 400 kilonewton. Determine whether or not a bearing plate is required. Should we design a bearing plate for the beam, or, and if so, calculate its thickness. What is the thickness? And calculate also the area of longitudinal reinforcement as inclined at 20 degrees to horizontal, and the area of vertical reinforcement. So you need to calculate also the longitudinal reinforcement, and then the area of vertical reinforcement, your shear link, and then your main bar of the beam. So you need to use 40, grade 40, and still whether it is horizontal or vertical, both use 250 Newton per millimeter. Your main bar or your stirrups is 250 Newton per millimeter square, mass steel. And then your PY is 275 Newton per millimeter square, and cover to reinforcement is 30 mm. Your beam has 30 mm cover. So first, we calculate the net bearing width. Net bearing width is taken as a list of the three. These three, A, B, C. Among these three, we have done this before. Among these three, can take a look at example 1, if I'm not mistaken. So among the three, among the three is the bearing width. The first one is bearing width. Second one is bearing width over 2 times 100 plus 100, and the last one is 600, whichever the least. So in this case, the least would be bearing width divided by 2 plus 100, which is 250 mm. And then the net bearing length, you need to minus the ineffective length, effective bearing length. So you have your nominal bearing length 150 minus this is a constructional tolerance 6 meter is 15 mm. Okay, 7, so you add 1 mm and so on. And then you have also ineffective bearing of 15. You need to refer back to your table here. So yours is grade 30. Supporting members is grade 30, so 15. You also have tendon, so be 0 at the supported member. So minus 15 and then minus cover. Then you get your effective net bearing length is 90 mm. So based on these two value, you can get your bearing area, area, bearing area. So this is your bearing area divided by your N force here, N reaction 400 kilonewton. So based on this, for force force divided by area, you get your maximum pressure. This is your maximum pressure, which is larger than your allowable capacity for dry bearing pad, which is 0.4 times 40, 0.4, which is around 1.6. I'm not mistaken, 16, 16, 16, 16. You can click yourself. 16. So it is not enough. So you can put some conclusion there. Not enough. Less. Not enough. So use bearing plate with end cover, 30 mm. So there is a cover for beam. It's 30 mm. So your beam, so the steel plate start 30 mm. And then your maximum width of plate will be 300 minus 2 times cover, which is 60. So you get your maximum width of the plate is 240. And then you try 200 mm times 90 plate. So you propose this size plate 200 times 90. 90 is your bearing length. Bearing length is 90. Bearing width is larger. So effective bearing length. So this is area of plate. This is force. This is your end reaction. This is area of plate, which is 22.2 Newton per meter square, which is smaller than the allowable um, bearing capacity. This is based on equation 8.2 here. You look at the previous slide. Which one? Take a look at your previous slide. This one. For larger bearing plates, you're using larger bearing plates, larger than the concentrated load plate that we calculated in example 2 and 3. So you are using this. The allowable bearing stress is 1.5 times concrete grade divided by 1 plus 2 times plate size, plate bearing, plate width divided by the width. So based on that equation, this is your FCU, and this is your BP, your bearing plate, proposed bearing plate 200, and this is your B lah. So based on this value, you get 25.7, which is larger than this, and it's okay to use this plate. Because if it is too high, then you need to increase your bearing size, the plate size, plate size. You can try to match it if you can, if it's possible to close to each other. So once that happen, your design will be more economical. You won't be using such a large plate, just enough for to match the bearing allowable bearing capacity. And then you want to determine your horizontal forces, because this time you want to design your reinforcement. So H is equal to mu V. So you take 0.7. We take 0.7, as you can see, concrete to concrete, both hardened. So it's 0.7 value of mu times 400. Because this is a pre-stress, there will be cracking. So you calculate your mu prime. Mu prime 7 times 4 times 400 times 300. You can see your equation. This is your AC, area of concrete. This is your value of H, and this is your value of H. This is your area of concrete. 400 times 300. 400 300 is your precast beam. 400 times 300. So this is your new mu value, new prime value. So so plate thickness we check for a bearing of the plate, bearing bearing of the plate. So basically the force. Uh, this is the force. This is your F, and reaction force. So and reaction force. You want to find the plate thickness is you divided by the, this is the E, modulus of the steel plate, the Young modulus steel plate. This is your breadth, and this is your mu prime. So what you get is the thickness. So basically you are like crushing the plate. So the force here 400. So you want to see how much is the thickness required to sustain the force of 400 kilonewton. So you have your 200 here. So B times modulus of elasticity for steel plate. So you get your thickness. Required thickness is 2.42, which is suffice if we follow the corrosion protection, which is for mm. But in the end, we propose 10 mm, 10 mm minimum as as suggested by the book by this book, 10 mm. So uh, you can protect the steel from corrosion, and then also from the horizontal forces. Next, we want to design the main bar, horizontal bar, which is using the 250 Newton per millimeter square of a Young modulus. So this is your end reaction F. So this is your numbers, 95% of your FYH, Young modulus of horizontal bar, and then this is the theta as specified by the question at angle of 20 degrees. So at angle of 20 degrees, we want to resist the horizontal force. And then times this is your mu prime. That's the equation. You can take a look. This is equation. This is your mu prime, theta, then FYH, and then divided by V. Very simple. And then you get your area, so you can specify based on this area. You provide three numbers of R16 bars. So you get your steel area of 603 mm squared. Then you design for your stirrup ASV, shear, shear, shear value, shear reinforcement. This is your H, basically here H, as you calculated before, your H. And then this is your 95% reduction, and then this is your FYV, then this is your mu prime. So calculate this, you get your 393 millimeter squared. So propose two pairs of R12 bars. You get your area of steel for ASV is 452, which is larger than this requirement. And then you can finish up with the drawing. So this is your design. You have steel plate here of 90 times 200. 90 times 200 steel plate, 90 times 200 steel plate, and then R16 bars is welded here, and then the plate is placed with 30 mm covered at both ends, and then three numbers of R16 as specified here, three numbers of R16 bars. So this is your design for horizontal, incline at angle 20. And then this is your reinforcement for shear link, which is you provide two numbers of R12. This is two numbers of R12. So that's all for your design of reinforced and plate reinforced concrete bearings. So next, we're going to take a look at bearing pads, which is commonly used in the site.